Okay. Yeah, my name is Marco, and I am a PhD student at MAR Data. And that is a grad school for educating marine data scientists in Germany. And today I'm going to tell you talk about some of my recent results I had. And the title is quite fancy: Layer-wise relevance propagation for echo-state networks applied to Earth system variability. And there's 3 buzzwords involved, and I'm going to go into detail for every one of them. So, as I said, I am interested in working on marine data, and in specific, I work on geospatial data. In my case, I try to train artificial neural networks on geospatial data. And the most important part of my PhD is then to open the black box and try to understand what the models have learned and how they come to their conclusion. And that's called explainable AI. Probably most of you know about that. So in this example, in these results, I show you I work with sea surface temperature fields. This is 2-dimensional data, of course. And yeah, you see the continents here. There's no sea surface temperature defined over land masses. So that's invalid grid points here. And I work with a phenomenon which is called El Niño Southern Oscillation. And this is every few years, there's some conditions where we find especially high sea surface temperature in the tropical Pacific. This is this region here. And that's called El Niño. Most of you probably know this term. And there's the opposite phase, since it's an oscillation, which is related to unusually low sea surface temperature in the same region. This is referred to La Niña. So from this rectangle box here, we can then define some ENSO index or El Niño Southern Oscillation index by just looking at the area averaged sea surface temperature anomaly in this box here in the Niño 3.4 box. Then we get an index over time, and the timeline is dating from 1880 up to today. And that's the region where we have measured real-world data. So it's quite a short timeline because we only work with monthly data. And we are interested in values, index values that exceed some threshold on the upside. So the red ones are El Niños, and on the downside, it's La Niña conditions. So we leave out the neutral states in between for this toy problem and just work with El Niño and La Niña samples as inputs and train a model on this index used as target value. So this is quite a simple classification problem we work with. And for us humans, it's quite easy to look at these 2 samples and discriminate whether we see El Niño or La Niña in the sample. And our aim is not to get some superior classifier here, but we are, as I said, interested in opening the black box and understand how the models come to their reasoning. So therefore, it's good to have this well-known simple toy problem here. So the first step is that we need a benchmark or kind of a baseline model, and we use a multi-layer perceptron for this case. And to use 2-dimensional image data as inputs, we just connect each grid point to an input unit. So that gives us a huge input layer. We have 2 hidden layers in between of 8 units, and then 1 output unit that predicts the final model output trained on the target value. And then the idea of layer-wise relevance propagation is to take this final model prediction as total relevance and then trace it back through the layers and attribute a small portion to each unit of the hidden layer, go back another hidden layer until we finally reach the input layer. And then we can have some sort of relevance score attributed to each and every single grid point. And this can then be reconstructed to get a 2-dimensional heat map showing us the relevance of each input pixel for the model to come to its conclusion. So the result for the multi-layer perceptron looks like this. On the left-hand side, we see the input or the mean inputs sample. Again, this tropical Pacific region is of interest. And on the right-hand side, you see the mean relevance map from our multi-layer perceptron. And this red area is the area which is most relevant for the model. And there is no surprise, the model also finds the tropical Pacific Nino region most interesting. And that appears to be physically reasonable for us and shows us or proves that the model did a good job in classifying these samples. Okay, cool. So now we have a baseline. The problem about multi-layer perceptrons, even in this very simple form, is that they have a lot of trainable parameters involved. And as I told you, we only have like 1,000 training samples, but the model already has like 88,000 trainable parameters. And that is might be a problem in terms that the model sometimes just memorize the input samples and tend to overfit, not really generalize well on unseen data. So for this reason, I was looking for alternative model architectures, and I came across echo-state networks, which is a certain type of recurrent neural networks. And the basic idea, I'm going to go into detail on the next slides. The basic idea is to have an input layer, an output layer, and in between we have a reservoir of just sparsely connected, randomly initialized units that can have recurrent connections. So originally these were designed for time series prediction problems, but in our case we want to do image classification. So we have to find a way how to feed two-dimensional sea surface temperature fields into the model. And one promising approach is to slice our input samples into columns. We could also do it and slice them into rows. It doesn't really matter. In our case, we picked to slice them into columns. So every column then becomes one time step. So we turn the X dimension or the longitude into the time dimension and keep the latitude or the Y dimension as the input or the feature dimension. So we got the input features over T time steps. In this case, it's 180 time steps to feed into the model. So how does it look in detail? So we have these time steps to feed into the model. And whenever we feed something in the reservoir, it unfolds its dynamics. And that can be characterized by this state transition function. And I don't want to go into too much detail, but there's 3 parts involved in the reservoir state transition. So xt denotes the reservoir states for time step t. And the first part is that it just keeps a fraction of the previous time steps reservoir states. So 1 minus some constant alpha, which is called the leak rate. We're going to come back to the leak rate later, so just keep it in mind. And then we add alpha times some activation and some huge term here. And the first part inside the activation is the current time steps input. So there we find u for time step t times some input weights plus some input bias terms. And the last part is that we have the reservoir recurrence, which is the previous time steps times the reservoir weights plus some bias terms again. So it's not too complicated, I hope. And then we feed 180 steps into the reservoir. And at the end, we get the final reservoir states, X capital T, here, X capital T. And then we have a simple regression problem, regressing these final reservoir states onto desired target values, Y capital T, that's the output target values. So this is just a linear regression problem. And the only thing that is trained for such an echo-state network is the output weights and the output bias. All the other weights, the input weights and the reservoir weights, are just randomly initialized and then kept fixed over the whole process. And this can be done in a closed form solution. So linear regression is not that fancy. We don't even need stochastic gradient descent or backpropagation or any of these learning algorithms usually involved in neural networks. And like this, we only have 301 trainable parameters because we have 300 reservoir units and one additional bias term. And that is already a big advantage over the MLP, where we had 88,000 parameters, you might remember. So, but then comes the problem, or the now we need to apply layer-wise relevance propagation, which is our contribution because it hasn't been done before. And therefore, we need to unfold the whole reservoir dynamics in time. And each time step then is treated as a single layer. So here I try to sketch it. So there is a lot of dots involved. So we got 180 layers. And yeah, well, let's go through it step by step. On the upper hand, upper part, you see the transition equation again, and how we train the output weights here with the final reservoir states. And that's where we start. We start with the final model prediction as total relevance, and then attribute it back to the last time step here. And then we go back. The lower track of the sketch is here, the blue part in the state transition. It's where we keep a fraction of the previous time step. And this is the most interesting part for us, the red one, is where we attribute some relevance scores to each time step's inputs here. And this green thing here, that's the input time step for capital T, and we got the green inputs in every single layer or every single time step. And these relevance scores can then be composed back to a two-dimensional heat map again. And the result is shown here on the right-hand side for our echo state network. Before we look at that, we go back to what we've seen before. That was the multi-layer perceptron, the mean relevance map with the strong focus on the Nino region, and only there. We don't see any significant relevance anywhere else. That's quite different for the echo state network. We also see the model highlighting the tropical Pacific, which appears to be reasonable to discriminate El Nino from La Nina samples. But we also see some stripes here, horizontal stripes, which differ for different model runs. And that already gives us a hint that it's model-related artifacts. But most interestingly, we find highest relevance on some area here between South Africa and Antarctica. And that cannot be explained so far that it's so relevant for an El Nino or the ENSO problem. And that is stuff that is currently investigated by us in further research. But so far, we find that we can apply layer-wise relevance propagation to echo state networks and also get some reasonable results at least. So the reason why we can achieve this is that we set the leak rate appropriately. As I told you, that's the crucial parameter in the state transition function. And this acts as kind of a memory parameter for our reservoir. We feed the samples from the left-hand side to the right-hand side. So we start at the other left side and start with these columns and feed column, column, column until we reach the right-hand part. And the model needs, or we want to make sure that the model equally involves all time steps. And therefore we need to choose alpha correctly. 0.01 seems to be a good choice to have almost perfect classification accuracy. And here's what happens when we increase the leak rate or change the memory parameter. Then the memory fades away. The model doesn't really remember what it has seen on the left-hand side. The relevance is focused on the right-hand part. And that can be driven to the extreme if we increase alpha to 0.2 or even to 0.4, where the model only really encounters the right-hand part of the input samples. It doesn't really remember what it has seen in the tropical Pacific. And therefore the accuracy drops to about random guessing. So it's kind of like a radar sweep that is scanning the input samples. That's what we found. But what we were also interested in is some kind of permutation experiment. We see that this is a really strong zonal structure here for this El Niño pattern. And we ask ourselves if this whole classification thing with echo state networks only works because we have this long and thin structure in this tropical Pacific area. And to try to prove that our echo state network is stable, we just applied some random permutation on the input samples and just destroyed this structure and wanted to see if the model still is able to classify the patterns and still find some reasonable relevance maps. So this is then the mean relevance map we find for El Niño samples. And of course, it's also permuted. And so we need to reverse the permutation, which can be done. The model has perfect classification accuracy, and also the mean relevance map can be restored and resembles the first one we obtained without permutation. So this model is stable. It doesn't really matter in which, how we feed the columns into the model. They can be permuted. It doesn't really destroy any performance. All right, so this is what I have presented in my paper published there. And the next step is for us to look at these structures here and the stripy things. Is it artifacts or is it facts? What does it tell us about the models? Can we use it on other geospatial problems? And also we want to go back and use echo state networks the way they were originally designed to, which is for time series classification. And instead of feeding two-dimensional samples of geospatial data, we could feed a bunch of indices, climate indices, for example, about the Southern Annular Mode, North Atlantic Oscillation, El Niño Southern Oscillation again, or some sea surface salinity indices, and then have t-time steps and a bunch of features and feed them into the model and try to make some useful climate predictions with it. That's also ongoing research. So to conclude my work, I've already given you some further work ideas. Well, we find echo state networks to be quite efficient in a way that we can apply them for image classification, and we only need less parameters, significantly less parameters. And these models are really, they can be trained quite easily and give us some reproducible and stable results. And have good prospects to be used on other climate problems because of their few number of trainable parameters, which avoids these models from overfitting on limited training data. That's it so far. Again, I'm really happy that I could join you at least online. And if you have any questions after this conference, feel free to get into contact with me. Thank you so far. And if you have any questions, I'm happy to answer them.